and we're going to use them to solve inequalities. Equations and inequalities. So find logarithmic and exponential equations and inequalities. So this, in some sense, is nothing new. We've done equations and inequalities before. It's not all that different. We're going to just use the properties of log and exponent to solve these things. So let me just give some examples. So here's one that you could call like the variable is in the exponent. Some examples of this case. If you have something like e to the 2t minus 5 equals 5,000, right? So the variable is in the exponent, and previously we wouldn't be able to solve this equation, but now we can, right? What do? We have something like this. You take the natural log of those signs, right? Take the natural log of those signs, we get natural log of e to the 2t minus 5, right? Natural log of e to the 2t minus 5 is the natural log of 5,000, right? Then we use the fact that these guys cancel each other out. Natural log and x are inverse functions, right? And then you solve for t, right? Now you're back in a very simple case, right? You solve for t. T is going to be equal to natural log of 5,000 plus 5 on the b over 2. Right? So the variable is in the exponent, so we pull it out. We pull it out using the log function. Okay. I'll put up some other examples, and then we'll do them. Another kind of example, a bit slightly more complicated. E to the 3x is 10 to the 2x times, say, 2 to the 1 minus x. Okay. Again, this is an example of the exponent. The variable is in the exponent. Okay. Another kind of example, you have the variable inside the log. So, for example, log base 6 x plus 1 is equal to 1. Right? So the variable is in the log, and to pull the variable out, we just have to get rid of the log. Right? Just like here, we had something in the exponent. Well, we had to get the exponent out by canceling off this exponential function. Right? So what do we do in this case? Carol?
6 to the 1 equals x plus 1.
Right, 6 to the 1 equals x plus 1. Right, so this is the same thing as saying that 6 to the 1 is x plus 1. Right? So x is equal to 5. So what Caroline did was translate this into the exponential form. Right? 6 to the 1 is x plus 1. Another way you can think about it, and it's entirely equivalent, is to say, well, let's take 6 to both sides. So 6 to the log 6 plus 1 equals 6 to the 1. Right? It's exactly the same thing. Apply 6, feed these guys, which are the same thing, into 6 to the x. Right? And then 6 to the log 6, 6 to the log, and log 6. Log base 6 cancel each other off, and you get x plus 1 equals 6. It's exactly the same thing, just in a slightly different form. Okay, and here's a slightly more complicated example, saying log base 6 of x plus log base 6 of x plus 1 is equal to 1. Okay. in the exponent. There's a variable in the log. There's another one. It's not really, well, you can call it a disguised quadratic. Disguised quadratic. So you can have something like this. Natural log of x quantity squared is equal to 2 natural log of x. Okay, but I think this is not that ideal a way to present it. So let's go back actually. So let's instead of giving all these different examples and then going, let's go one by one. Okay. So okay, so let's go back here to the variable in the exponent case. Okay. So here's the simplest example. We just cancel off. Okay. So what do we do in this case? Here's the second example, slightly more complicated. Right? E to the 3x is equal to this thing, and the variables are in the exponents. There's just more of them, right? So it's not all different. What can we do? Right? In the first case, we took the log of both sides. Second case, go.
So you can take the natural log.
Take the natural log of both sides. Right? We're going to try to pull the exponent out. So we've got e to the 3x equals 10 to the 2x, 2 to the 1 minus x. Right? Okay. So we take the natural log of both sides. Right? We get natural log of e to the 3x is equal to natural log of 10 to the 2x times 2 to the 1 minus x. Okay. Certainly if a equals b, then natural log of a equals natural log of b. Because a is b. So now what do we do? Well, in this case, we've already seen what we do. Right? You can pull the 3x out. You get the natural log of b. That's 1. You just get 3x on the left-hand side. And what do we do to the right-hand side? Sorry? What do we do with the right-hand side? We've got the natural log of this thing. We've got a natural log of the product. Do we know anything? So your neuron should be firing like natural log of the product.
What rule would apply?
Yes.
So okay, it would be ln 10 to the power 2x plus ln 10 to the power. Sorry, I was just blanking out.
That's okay. That's okay. Okay, and then now we've got natural log of something to power. So we what? So
You took so
take
it's
the
2x
two.
ln 10.
Okay, and then the question is to solve for x, right? We need natural log of 10 plus natural log of 2 minus x squared. Okay. So now the question is to solve for x, and now you've returned to junior high school. Okay. Solve for x, right? It's easy, right? It's the only thing is that the numbers are, you've got more fancy looking numbers. Right? You've got, if somebody said 3x is equal to 5x plus 2 minus x, and said solve for x, you would laugh. Right? You should be laughing now because this is the same thing. Right? It's just that instead of 5, we've got 2 natural log 10 of x. Right? This is really nothing. Right? Okay, so let's, you know how to do it. Let's move all the terms involving x over to this side. Right? We get 3x minus 2 natural log of 10x plus natural log of 2x equals natural log of 2. Right? You take all these things, you factor out the x, just as you did in junior high school. Right? And then you divide both sides by that factor. So x is natural log of 2 over this. So, it looks more complicated, but in fact, there's nothing to it. The only thing that was added was your junior high school algebra.
Where did so on the denominator, y is -2 ln of 10?
So it should be.
Okay.
Could you do natural log?
Yes, that's also fine. You can move the 2 inside of your natural log of 10 squared. Okay. Everyone all right with this? Everyone all right? Okay.
Well, yeah.
You look dazed or is it really okay?
Yeah.
Okay. Okay. So now let's do. Remember the second one was the variable in the log, right? And the example. We did one example, and then we have the slightly more complicated example, which probably will not be all that complicated. So here it is. And so you remember in the first example, all we did was take the x of both sides, right? We took e to, we had a equals b, and then we hit the thing with the exponential function, right? And we're going to do basically the same thing here. Okay, but maybe before that, what should we do before that? What might be a good thing to do before that? What might be a good thing to do?
Make it one term.
Make it one term, right? Because right now we've got the sum. It'd be nice if we had on the left-hand side log of something, right? Because then when you take x, then we just cancel each other out and you're left with something. Right? So that would be nice to do. And so we use our properties of log, right? Who would like to tell me the properties of log? It's not beneath you. Caroline?
So it would be log 6x times x plus 1.
Great. 6x plus 1. Okay. This is the same thing as that, right? Okay. And then we get so we take x of both sides, or we follow Caroline's lead and say, well, this is the same thing as x plus 1 equals 6. Right? That's probably the cleanest way. Log base 6 of this is 1, means that 6 to the 1 is this. Right? And so we get x squared plus x minus 6 is equal to 0. And so x plus 3 minus 2 is equal to 0. And so x is going to be either minus 3 or 2. Okay, so right, everyone okay?
I should understand the second step.
Sure.
Log 6 and then you multiply x into x.
So remember, whenever we see something like log base b of y equals x, remember we said that this is the same statement as saying that b to the x is y. Right?
Well, is it the same thing as, well, you know how yesterday we learned about the errors, not to make those errors, like if you have log, I don't know.
Yes.
Yeah, is that the same thing or is it just different?
This is not one of the errors.
I mean, in the errors too, it's kind of like the same thing. If you have like, they said if you have log base something and then log base something, and if you add both of them, it's not equal to bracket and then you add them.
Right. What it is equal to is log of the product. Right?
Oh, okay.
Right? We haven't made, it would be wrong if we said that this was log
X
of
plus.
x plus. That would be
Okay.
completely wrong.
Alright.
But what is true is that log, so it's not true that the sum of logs turns into the log of the sum.
Okay.
What is true is that the sum of logs turns into the log of the product.
Okay.
Okay. And that's actually the great property. that log takes products and turns them into sums.
Okay.
That was sort of why log was so useful. Okay. Okay. So is everyone else okay? Everyone okay with this? Okay, except that there's something wrong. Okay, everyone is okay, but actually there's something wrong with this. What's wrong? How is it?
X can't be -3.
X can't be -3, right? Because we're taking, we want it to satisfy this equation, right? Log of x plus log of x plus 1 should be 1. But we put in a -3 there, we get log of -3, right? There is no log of -3, right? Remember what the log function looks like, right? The log function is defined on positive real numbers. Right? This is log of speed, but at least speed are bigger than 1. Right? So when we were here, there was an implicit assumption that x had to be 0 and x plus 1 had to be 0 also. Okay, so so when we combine these together, we basically introduce an extraneous root. Okay, so it's just like before, we introduced some sort of extraneous solution was introduced. Okay, so with this sort of thing, you have to check at the end, or you have to be aware from the beginning where your inputs can lie. Okay. The domain is x has to be bigger than 0. Okay. And here is x bigger than -1, but as long as x is bigger than 0, you're bigger than -1. Okay, so this is not a solution. Okay, but this one is. Okay. Okay, so there are a couple more examples. Maybe we'll do a simple one first. Number 7, natural log of x is 2.
What type is this? This is the same.
This is actually not any of the types. This is just sort of like an afterthought. It's like an iteration of a type. So this is sort of like the variable is in the log of the log. Right? So it's a natural extension of the previous example. So,
Can I ask a question?
yeah.
So would this be just the natural log times the natural log is e? Yeah.
This isn't a times, this is a composition, right?
Oh.
You got the natural log of x.
Okay.
So, if you had one log, you would eliminate it by using the exponential function. So now you've got 2 logs, so you've got log, so what do you do? So,
Would you say that e squared is natural log x?
well, let's see. Oh, yeah. Okay, so you could translate that. You could say, well, this is the same thing as saying that e to the 2 is natural log x.
And then say that e to the e squared?
E to the 2 is x. Yeah. Okay. So you do the same thing that Caroline said. You translate it, right? This is log base e of something is 2, right? That's the same thing as saying that e to the 2 is that something, right? And that something was log base e of x. Right? And then you do it again, log base e of x is something, so e to that something, sorry, so x is e to that something. Right, so you just do the same thing twice, right? Right, it's easy, right? you get to the object when you take the coat off. Two coats, you just take the first coat off and then the second coat off. That's all. That's it. Right? Natural log of natural log of x equal to. Another way of looking at it, and like I said, this is the same way. It's equivalent. You take x e to this, right? E to the 2. So you get natural log of x is e squared, and you do it again. Right? E to the natural log of x is e to the e squared. That's the same. X equals e to the e squared. Right? And once you're comfortable with it, you don't even have to think about it. Right? You just say that this is if you have two natural logs, then you just put two x's on it. Right? So you're saying x of natural log of x is x of x of 2. Right? In other words, x is e to the e to the 2. Right? So nothing at all going on here. Okay. And is everyone all right with that? Who hasn't had natural logs before other than Strauby? I know Strauby has. Okay. Then I'm going to ignore, as I said last time, I'll just ignore everybody else. Talk only to Strauby. No, it may be that you guys need to review. Okay. Okay, so like I said, there are also these sort of slightly tricky examples, but really it's not all that tricky. It's just that they take something and they try to make it. This is like an effort, a sort of contrived effort to make the problem a little bit more interesting. Natural log x 1 squared equals 2 natural log x. I guess I shouldn't make fun of it. This sort of thing does occur, actually. Okay. So you see it, and you say, oh, okay. Well, the professor said, use the term hidden quadratic. There's got to be a hidden quadratic in here. Right? This has got to be some sort of quadratic equation. There's got to be some sort of quadratic equation. Like, where's the quadratic equation? Melissa, where's the quadratic equation? Where is it? You see it. Where? No. Remember, it's a quadratic equation, right? It's something like something squared plus something plus a constant equals 0, right? Right. And then you try to solve for the thing that is squared, blah blah blah. Right? Well, what do you see here that looks like that? What is y? What should we let y be? Joanne? Did you say that? I thought you said move the 2 out. But
No,
maybe-
move it over. Subtract.
Oh, okay. Okay, so natural log. Sorry, I misunderstood. Okay. And then?
And you can pull out the ln x.
Okay. Yeah.
Wouldn't ln x squared minus 2 ln x, couldn't that be written as ln x squared minus ln x squared equals 0?
Yes, but that's a little bit trouble. So you're saying that you could write it like this: ln x quantity squared equals natural log x squared.
Oh, got it, because it's not quantity.
Not the same thing.
Oh,
Not the
okay.
same.
Got it. Okay.
Yeah. Okay, and then what happens? Okay, you solved it, right? You've broken it down. by the zero, if you want, by the zero product property. If the product equals 0, then it must be that one of the guys, one or both of the guys is 0.
Can you go over how you went from that to the last step?
Sure. Actually, let me make it more obvious what the quadratic is. So let y be natural log x. Then this equation we rewrite as y squared is equal to 2y. Okay. This y squared is equal to 2y. Are you good at Alice? You know as well. Sorry? Yes.
So, you know how ln x, the whole thing is in squared? I mean, the whole thing is squared, right? Ln x. I thought you weren't supposed to take down the 2.
You can. No, we haven't done it. We've just written it here. Y squared, natural log of y, quantity squared is 2y. Okay. So somebody gives us, here's the equation somebody gives us. Okay. Here's the equation somebody gives us. Natural log of x, quantity squared is 2 natural log of x. Okay. This is not true in general. This is not true in general. We're not saying this is true in general. What we're wondering is this true for some x? Is there any x for which this is true? Okay. So yeah, so this is not, please don't say like, oh, natural log of 1,000, well, 100, that's going to be 100 natural log x. That's not true.
Okay.
In general, that's not true. But it might be true for some numbers, and let's find out for which.
Okay.
Okay. So we say, okay, well, y squared is equal to 2y, right? In other words, y squared minus 2y is equal to 0. Y times y minus 2 is equal to 0, right? And what does it tell us? That y either has to be 0 or y has to be 2. Okay. Going back to our original term, that's just saying natural log of x has to be 0 or natural log of x has to be 2. Okay. Well, what do you say to that? Caroline?
You can only use the 2 because anything to the 0 is 1.
Right.
So if that was the solution, it would violate the horizontal line.
Yeah. So, natural log of x is 0. Well, no. Actually, it's okay. They're both good.
Just use x.
Yeah, no, that's fine. That's fine. Right. You hit both. So let's write it like this. So, right. Or natural log of x is 2. So we see, okay. Take e to both sides, right? So we get x is equal to e to the 0, or x is equal to e squared, right? X is equal to 1, or x is equal to e squared. Okay. So for those two x's only, is this equation true? This equation is false. It's not a general formula, but it's true for these 2 points. Cool. Okay. 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 Another example, this is problem 27 in the book. E to the x minus e to the minus x equals 1. Okay. Okay. Suppose you have this. What might you do with it? I'll let you guys think about it for a minute. Okay, try for 1 minute, see if you can get anywhere on this. This one involves a slight trick. So you have to be a little tricky to do. Okay, does anyone know the trick? Hey, Lauren, no, I got change, yeah.
Sorry, take the natural log of each side.
Take the natural log of each side. Okay, we can try it. Natural log of e to the x minus e to the minus x equals natural log of 1. Okay, and then what?
Then that side would equal, because 0.
The right hand side is 0. Yeah,
Yeah.
natural log of 1 is 0.
Yeah.
But
Then that would be the quotient of each one. So it would be natural log of e to the x over natural log to e to the negative x.
no, right? Natural log of, so natural log of the quotient, right, is the difference of the natural logs, right? But here, you committed one of the errors. Right?
Yeah.
Okay. This is the natural log of the difference, not the difference of the natural logs. So, so you invoked a property that this thing doesn't have, unfortunately. Katie, what are you going to say?
What?
Did you raise your hand? Sorry?
I don't know if this is right, but I just did e to the power x minus 1 by e to the power x equals to 1. And then that's something
E to the x.
minus 1 by
That's certainly,
Yeah, is that right?
I mean, that's certainly true. That's legal. You haven't done anything illegal. Yeah.
And
And
can
then,
you just solve it, like, making it into one fraction, and I don't know.
okay, let's see. I don't know. Let's be, I mean, as long as you don't do anything illegal, it's okay. E to the x, right? So you're going to make it into one fraction. E to, multiply this guy by e to the x also. And into 2x minus 1 over e to the x.
Yeah,
Right?
and then you can take e to the power x to the other side.
Mhm.
So you're going to start this.
Right. Great.
Okay, I don't know what to do.
Okay, so now let's put it all on one side. E to the 2x minus e to the x minus 1 is equal to 0.
So that's a,
That's a quadratic, exactly, right? You've got something squared minus that something, Right? So let's let our y, again, be the thing that gets squared, right? This is y squared minus y minus 1 is equal to 0. Very good stuff. Okay, and then you say, okay, well, you solve that using the quadratic formula, say, by quadratic formula. You know that y is going to be, negative b plus or minus the square root of b squared minus 4ac over 2a, right? That's 1 plus or minus root 5 over 2. Quadratic formula. Okay, and so that tells us, going back to our original guy, e to the x is plus or minus root 5 over 2.
Where are you getting these numbers from?
Which numbers?
Wrong thing.
Which numbers?
Like 1 and 4.
One, this is the quadratic equation, right? You've got
Yeah.
y squared minus y minus 1, right? So here's your ax, a, b plus c, right? So negative b, right? Negative 1, plus or minus the square root of b squared, that's negative 1 squared, minus 4 ac. AC is minus 1, so we get minus 4 minus 1s. So that's plus 1. And then divide by 2. The quadratic, it's just the quadratic equation. And then we get to here. Okay, so and then we say, okay, well, does anyone see, is there anything wrong with these equations? Anything wrong with these solutions? Well, there's a little bit of trouble because root 5 is bigger than 2, right? And we get 1 plus or minus something bigger than 2. When we get the minus guy, we get a negative number, right? E of the x, as we know, is never negative. And so, you know, one of these guys is going to get the minus guy is going to get. So, 1. Right, so, 1 extraneous solution. Okay. And then to get x, of course, we take the log of both sides and we get that. This thing is the natural log of 1 plus root 5 over 2. Okay. Any questions? Sorry, there's a guy in the tree up here. Any questions? Don't look. Okay. Okay. So we don't really have time to do all of the second part of this section, but we should at least get started. So equalities, right, involving using log and stuff. So there's one thing you got to watch out for. One warning. Right. If b is greater than 1, then log and these two functions preserve inequalities. Right? That is, right. If you have a is less than b, then b to the a is less than b to the b. Log base b to a is less than log base b to b. Okay. But if b is between 0 and 1, then they reverse inequalities. Okay. Like a less than b would imply that b to the a is bigger than b to the b. Okay, and same for the log.
What do you mean by preserve?
Exactly this. i.e., that an equality, when you hit it with the b to the x function, still keeps the same relation.
Okay.
But if b is smaller than 1, then the relation gets reversed.
Okay.
Okay. Log base b to a would then be bigger than log base b to b. Okay. So, right, and the reason is actually simple. Why? Because, like, if b is bigger than 1, then what does the exponential function look like? B to the blah. B to the blah looks like this. Right? Right? B is increasing. Right? If b is less than 1, then we have the opposite case. B of x is decreasing. Right? So think, right, if you have 2 points A and B, what's the relation between B to the A and B to the B? If A is less than B, here's my function. B to the A, is it bigger or smaller? Smaller, right? B to the A is smaller than B to the B. And similarly, if A is less than B, over here, what's the relation between B to the A and B to the B? B to the A is bigger. B to the A is bigger than B to the B. Right? And so that's why, if the base is smaller than 1, then this relation gets reversed. Right? If B is bigger than 1, then the relation gets preserved. So let's do at least one simple example. Okay. So 2 to the x is bigger than 10. 2 to the x is bigger than 10. So we'll hit this thing with a log, say. Natural log 2 to the x then is bigger than natural log of 10. Right? Because the base that we're using here is e, which is bigger than 1. Right? And so we get x natural log of 2 is bigger than natural log of 10. And so x must be bigger than natural log of 10 over natural log of 2. One more example. This is problem 53. 4 times 10 minus e to the x is less than -3. Okay, and we can do this however you want. Maybe anyway, let's multiply through by 40 minus 4e to the x is less than -3. So we get, I'm going to move this guy to this side and this guy to the other side. So we get 43 is less than 4e to the x. Right? So e to the x is greater than 43/4, right? And you take natural log of both sides. Natural log of 43/4 is less than x. Nothing fancy. We'll start off next time with some more complicated examples that use some of the things that we